welcome to the talk.
Okay. Yeah.
Sorry.
Can you do something?
Oh.
Sorry.
Okay. Thank you, Bruno, for inviting me here today to do the talk. So today I'm going to give a talk titled Concentration of Quantum Equilibration and an estimate of the recurrence time. So this was done in collaboration with Nathan Pagliaroli at Western University and Alvaro Alhambra at the Max Planck Institute for Quantum Optics. And you can find the work on arXiv right now. So this work was completed at the end of my PhD, McMaster University, where I was also an associate graduate student at the Perimeter Institute, and I've joined Nottingham as of Monday. So the overall theme of the research, or the big question that I want to answer, is how does statistical mechanics emerge from unitary dynamics? So behind that statement, there's a lot of nuance and open questions, but for today, and usually in my research, what we'll do is we will set our sights specifically on isolated quantum systems, and my work usually focuses on systems with finite range interactions. Most results I will showcase today, however, don't actually require locally interacting Hamiltonians. So we usually write our Hamiltonian in the following generic way. So lowercase h subscript x just stands for some interaction somewhere on the lattice. And we will, throughout the talk, label our energy eigenstates and energy eigenvalues in the following sort of standard way. So to further clarify, we usually have in mind lattice systems with local interactions and finite local Hilbert spaces for each site on the lattice. So the models to sort of keep in mind during the talk will be Hubbard type models, spin models, and so on. And of course, time independent. It's usually a time independent Hamiltonian. And so these are typical. So these are interesting testing grounds for the ideas that we're interested in, as well as having, of course, a lot of physical significance. So they are typical models of magnetism, electronic systems, and importantly, sometimes they can be studied in cold atom experiments. So before we get started on the topic completely, I will be showing numerics throughout the talk. So for full transparency, and perhaps an advertisement of my numerical background, I will be showing, I'll briefly discuss the model and plots, the model that I'll use to generate the plots and the videos that I'll show today. So we'll be working with this Heisenberg type model with nearest and next nearest neighbor interactions. So we also take this model to be translation invariant. And so by resolving the symmetries of the model, we can exactly diagonalize the model for up to 24 lattice sites. And so I chose this model for a few reasons. One, it's been recently featured in a few studies investigating the eigenstate thermalization hypothesis, showing that the non-integrable limit of the model appears to be converging to the ETH ansatz that I'll discuss later. And secondly, it's always nice to have some extra lattice sites on your plot. So we will stick with the parameter regime of this model, where we will be using a non-integrable model. So this talk doesn't feature lots of integrability. So of course, with a model in mind, we need an observable and a state to time evolve. So we pick the following observable, which is a sigma z matrix on the first lattice site. The interesting thing about this observable is that it's actually not translation invariant. So you actually have to work with multiple symmetry sectors to evolve the dynamics correctly. And we will choose the following simple Neal type state, which is anti-parallel spins with their neighbors. And this is a product state. And importantly, for convenience, this mixes only two translation symmetry sectors. Okay, so getting into the story. So the typical story of the emergence of statistical mechanics from unitary dynamics is the following. So suppose we initialize our system in some pure state psi, then we can decompose it in the energy eigenbasis in the usual way. From here, we see that the global state itself will not go to equilibrium as it's just a vector. So what we do is we usually introduce an observable, usually a local one, and we track its evolution in time. And now we expect that if we wait long enough, this observable's expectation value will relax to some equilibrium value. So this is, however, of course, somewhat of an abusive notation. Our observable's expectation value does not have such a limit. We can't take the limit as t goes to infinity because our function is an almost periodic function. So instead, what we do is we introduce the diagonal ensemble, which is the infinite time average of our state. And so if our observable relaxes to equilibrium, that equilibrium expectation value will be given to us by the diagonal ensemble. So just for some intuition here, this will go. We have the dynamics of our example for the viewing experience. The key takeaway here is that, at least in the example that I chose, equilibration is actually quite quick. So we start with one spin up, and quickly we relax to the expectation value of 0. And note this isn't always the case. It's quite easy to construct examples of equilibration where the timescales scale quite poorly with the system size, but the observable and state pair that we chose here today eventually becomes system size independent. So these dynamics were generated with 22 lattice sites, and it's kind of hard to see fluctuations around equilibrium by the end of the plot.
Sorry, John.
Yeah.
And that's just, there's no time average there.
There's no time averaging. That's just the, yeah, on the y-axis you just have the observable. Yeah. So we don't just expect the system to go to any equilibrium, we expect it to go to thermal equilibrium. And what that means is that we expect that the equilibrium value given to us by the diagonal ensemble will agree with the thermal average, which is characterized by some inverse temperature beta, an appropriately chosen inverse temperature beta. And so this is, of course, usually argued to hold based on the eigenstate thermalization hypothesis, which is written here. So this is a hypothesis, or sorry, an ansatz on the matrix elements of our observable A. In particular, E bar is the average energy, omega is the frequency, and R is a random variable with 0 mean and unit variance. So this has been investigated in many studies and verified in several numerical studies. So roughly speaking, we can classify the types of problems in this research direction into 3 sort of dynamical regimes. The first being equilibration. So does such an equilibrium exist? And if so, how long does it take for us to get there? We do have strong criteria for when equilibrium should emerge, and I'll talk about that later, but in general, we are lacking a clear understanding of relaxation dynamics. And we can't, for example, predict equilibration timescales based on initial conditions of your system for any class of interesting states in some class or in some class of non-integrable models. But we have, for example, making some progress for free systems. So the next regime is the equilibrium regime. Assuming that we get there, can we describe that equilibrium with the usual ensembles of statistical mechanics? And this is usually explained using that eigenstate thermalization hypothesis, as I said, but we don't have any general proof that singles out any class of models for which ETH should be true, but there's ample numerical evidence that it should be there. And the third regime is one where we have recurrences to the initial conditions. So will our system actually stay in equilibrium, as the name equilibrium should suggest, or will it leave equilibrium? And of course, the answer to that is it will eventually leave equilibrium. That's guaranteed, but those recurrences should be pushed out very far in time. So there's lots of missing ingredients to understand each of these three classes of problems, but today we'll focus on the first and the third category, meaning we will, for today, forget about the thermal average. So to summarize, the talk today is focused on our path to equilibrium, how strongly the expectation value concentrates about equilibrium, and we will investigate the lower bound on the recurrence times. So to put this on more mathematical terms, we might introduce a function like the following, f of t, which is a finite time average distance between the time evolution of our expectation value and its equilibrium value. And in general, we expect for the situations that we're interested in that f of t should decrease or go to 0 in finite time under reasonable assumptions on the initial conditions. So, of course, studying the average over time is likely to miss recurrences, so it's sometimes preferable to study the difference between the observable and the equilibrium value. Also, while I've talked mainly about pure state equilibration of some observables so far, there are, of course, other important and interesting dynamical functions that we might be interested in that have interesting properties as they relax to their own equilibrium value, if they do, like the fidelity, the dynamical correlation functions, out of time order correlators, and so on. In fact, interestingly, usually these functions are much easier to work with analytically than our pure state equilibration. So a lot of work has been done on equilibration, of course. So one major result is that if you let big T go to infinity, you can bound this quantity given to us by f of t by the following expression. So we have the largest singular value of a to the power of 2 times the trace of the purity of the diagonal ensemble. So this can, for example, be found in Short's article from 2011. So to give you some intuition, here is a plot of the purity of the diagonal ensemble for 3 trial states as a function of the system size. So we have the purity on the y-axis, and that's logged, and on the x-axis we have the system size, and you can see quite clearly that maybe by 16 lattice sites, the exponential decay should seem quite obvious. So we expect the purity of the diagonal ensemble to go to 0 exponentially fast in the system size. And of course, this is not true for all states, but for the states that we're interested in today, this will be expected to be true, and we'll take it for granted that this is true.
What kind of operator does that?
This is the largest singular value. So, of course, this is an infinite time result, and it would be desirable to try and make some amount of maybe some type of a finite time result. But this turns out to be extremely hard, both numerically and analytically. And so the reason for this is in part because we want to study an extremely large dephasing problem, as seen here. So we have the expectation value of our observable, subtracting off its equilibrium value, and this gives us these V alphas as complex numbers, which rotate around the complex plane with frequencies G alpha, and these are just sort of convenient compressions of our usual notation. So we have this big sum of complex numbers, and in some cases we expect the sum to go to 0 quite quickly, and perhaps this is as quick as, say, like a Gaussian function decaying to 0, and in other cases we expect there to be significant transport in the problem, and we expect the dephasing to take quite a long time, and the equilibration timescale to scale poorly with the system size. Let's play. So just for some fun and intuition, let's look at a time lapse of this dephasing that I spoke about. So in this video, we have the real part of the V's on the x-axis and the imaginary part on the y-axis. The time lapse here is done for 18 lattice sites, and it actually processes about 100 gigabytes worth of data, so that you can see at t is equal to 0, all of our V alphas lie on the real line, presenting a very atypical configuration of these complex numbers. And we will see a dense cloud form around equilibrium quite quickly. And so this is the same observable as the first animation. So we definitely don't need to watch the whole thing, but we see the cloud form around 0 quite quickly. Okay, so with how hard this problem is, we'd of course like to make some progress. And we will initially set up a scheme that doesn't actually discriminate against what type of dynamical function that we're interested in. So to do this, we introduce the following probability distribution function. So this distribution should be understood as if we were to randomly choose some time t, this function gives us the probability that the value of our function f of t is exactly x. And so the mean of our function is denoted here as f of infinity, and it's just the average of our function over all time. And importantly, the moments of the distribution can also be written in terms of this average. And so the main idea here is that studying these moments can reveal information about the equilibration process. And you'll probably note that kappa 2 here would just give us the case that appeared in the short bound for that inequality I showed you earlier on a previous slide. So now, in general, for the cases that we will study today, one can show that these moments can be bounded above by something like q times g, where g is some small quantity to the power of q. And so finding these bounds is more or less equivalent to solving the problem. Once you have these, all of the solutions to the problems that we solve sort of fall out, as you'll see. So here is I promise this is the last video. Play. So here's a quick video of P of x forming as we increase the interval in which we build it, or the interval at which we average over. And this is again for 22 lattice sites this time, and the same observable and state pair. And note that it appears that as we increase tau, what happens is that the distribution becomes peaked, highly peaked around equilibrium, and we expect the peak to become sharper and sharper as we increase system size and as we increase time. It's getting up there, and you'll just have to, we don't have to watch the whole thing. You also have to take my word for it that it becomes quite sharply peaked.
Question.
Yeah.
Just checking to understand. So you have the expectation value of A, which is the magnetization as the central site.
Yeah.
Yeah. As a function of time, and you're running for time tau, and this P of tau is going to do and sometimes it's called an empirical measure, in the sense that it's the probability of occupying values x that for some reason go from, I guess you cut off the -1 to +1 because you never see.
Yeah, because it's like so improbable to be there. So most of the probability weight is really close to 0. Yeah.
So these things should become smoother with time, and also will become, in the sense of these little fluctuations, and it will peak at 0. That's a statement.
Yes. So I don't know how, sort of, well, I don't know if we can derive some well-behaved nice function for it, but yes, yeah. So now potentially an enlightening way to get some intuition would be to appeal to the principle of maximum entropy for our distribution. So we can think of a thought experiment where we randomly select some time t and compute the expectation value of our observable. So conveniently, we will just set this to 0, as you can always do by shifting the observable. So then the variance of our observations will be given by sigma squared here. And ignoring all moments, which is equivalent to guessing that they are negligible, this gives us a Gaussian if we maximize entropy here. So note that we have sigma squared in the denominator of the Gaussian, which predicts, and sigma squared is related to the, or upper bounded by the purity of the diagonal ensemble. So we expect an extremely sharp probability distribution about 0 here. So now this line of reasoning is quite powerful. In fact, it's this line of reasoning that gets you to the fluctuation dissipation relation. So to get the fluctuation dissipation relation, we can, for example, investigate the conditional probability of A of t given some initial condition that we have as A of 0. And this would be given to us by the joint probability distribution divided by the distribution of the initial condition. And this was studied in Mark Srednicki's 1999 paper on thermalization in quantum systems. So you can't actually do this directly. Instead, what we will do is we will fix some time t and introduce a random time t prime, investigating the distribution for times t plus t prime and t prime. So to produce this distribution, or guess its shape, we will employ maximum entropy arguments again. The second moments for this problem are straightforward. The time independent ones are identical to the previous variance that we used for the single variable Gaussian. And the last second moment returns you a function of time, which is just an autocorrelation function. So when you maximize entropy, you get the bivariate normal distribution in this context, only considering second moments. Before we put all of that together, I'll introduce this autocorrelation function C of t, this time normalized, so that at t is equal to 0, it's just equal to 1. And then putting all of this together, we get the following conditional probability density function. And so this is a long equation, and the details actually aren't important. The key takeaway is the following equation. And so this casts the pure state evolution in terms of an autocorrelation function. And note that the probability argument is telling us that this equality holds with high probability. It is not an exact equality. And it's also tempting to potentially take a specific choice of t prime rather than a random choice, which would give us the following equation. And interestingly, this tells us the potentially pure state evolution is captured nicely by some autocorrelation function. So unfortunately, when you actually test this equation, it doesn't work. It does, however, work nicely for early times in some cases when you compare initial decay rates towards equilibrium, specifically when your initial conditions mean that you will decay towards equilibrium like a Gaussian as seen here. And you can see that the different forms of the decay rates here, sigma g is characterized by commutators with A in the Hamiltonian and the diagonal ensemble, while sigma A is characterized by nested commutators with the Hamiltonian and the observable, and then the expectation values taken with respect to the initial state. And so the fact that they are similar was found in another article of mine. And so the evidence for this relation is actually quite sparse. It currently exists more of as a proof of concept. However, it's true if you consider Hamiltonians or typical Hamiltonians, which are diagonalized by a random unitary matrix. And so one of the interesting parts of sigma g is that it was recently identified as a quantity that controls the equilibration timescales in a 2018 article. So here's a plot exploring this for two observable state pair examples. So on the y-axis, you have sigma g squared divided by sigma a, and on the x-axis, you have system size from 10 to 24 spins. This is in the same Hamiltonian that we had previously. You can see for one example in blue, we have pretty good agreement. In black, not so much, and in green, very much, not so much. So basically, what this plot is telling you is that it's easy to find examples where this relation between these two decay rates agree. It's very easy to find cases where it's satisfied, and it's easy to find cases where it's not. So it's pretty clear that more study is required to investigate this in the future.
Sorry, how do you define early time here? So for which times do you expect this relation to work again? Sorry.
Very, very early times.
So small compared to what?
To small compared to, let's say, one of the coupling parameters in Hamilton. The small compared to maybe the butterfly velocity. Or maybe on the same order of magnitude. Yeah.
So again, to try to understand. So you have a big approximated quantity, sigma A, sigma G at the bottom left.
Yeah.
And that's loosely saying that the time scale to relax from some non-equilibrium initial state, which was your null state, to whatever equilibrium is, which is controlled by sigma A,
Yeah.
is the same as the time scale to decorrelate a correlation function in A, which is the time scale sigma G. Is that correct?
I wouldn't go that far. So all I'm saying here is that these two functions decay towards equilibrium for some time regime, and the parameter in that argument of the Gaussian is sigma g, and in this one it's sigma a, and there doesn't seem to be a reason why they should be equivalent, but it looks that like under certain conditions that we can go into, like sort of the typicality or the lack of transport in the problem, these seem to be equivalent.
So,
Yeah.
sorry, I forget the exact detail of how you define C, but it seemed to me that C was a correlation function for
Yeah, it's an auto-
in equilibrium because it was integrating over T prime.
Yes, yeah, it's an autocorrelation function. Yeah.
So now, I mean, in general, the decay from a non-initial state, which is not the equilibrium state.
Yeah.
That's so classical stochastic, but it's understood, which would be A. In general, the time scale will not be the same as the time scale that controls decorrelation in the equilibrium state.
Yeah, yeah, I agree.
First, if the problem is simple and there is just one dominant rate,
Yes.
they would tend to be the same, but the more complicated they are, the less likely they are the same. So I would say,
Yeah.
no idea how this applies quantum.
So basically, I agree. If the problem is sufficiently simple, then you're right. And then if it's too complicated, then this treatment that I just went through is not sufficient. Okay.
Exactly. Just to add on that, because also here we are looking at times that for which our state is very far from it.
Yes. Yes.
So there is really,
Yeah, absolutely. So this is more of a story of failure than it is a story of me telling you something
yeah.
that is yeah.
No, that's a good point because you cannot even invoke like FET arguments because fluctuation dissipation is you give it a little kick.
Yep.
The relaxation is the same as the decay of correlations, but this is
Yeah.
non-linear response.
Yeah, exactly.
Yeah.
So the moral of the story that I'll get to is that for sufficiently easy initial conditions, those initial conditions will look more or less like linear response at early times. But if your states are too complicated or your observable is too complicated and there's sufficient transport or anything else going on in the system, then this description fails. Okay, so interestingly, with assumptions on the initial conditions and eigenstate thermalization, you can relate the autocorrelation function that Srednicki derived in his article to the Kubo formula from linear response theory. And so this was first demonstrated by Srednicki again in this 1999 article. And it's been numerically verified to hold for later times, not just early times. So this equality is for like in these papers, there's quite close agreement for larger timescales. So the Kubo formula will also initially decay like a Gaussian for the cases that we investigated, but instead now we have sigma k squared in the argument. And so we have the following form for that. And so this time it's characterized by thermal state, by the thermal state and commutators with the Hamiltonian and the observable. And we also numerically verified if sigma k agreed to sigma g, which is sort of like an independent test to see if the fluctuation dissipation relation would hold in our system. And so on the y-axis now you have sigma g divided by sigma k squared. On the x-axis, the same system sizes. And you see rough agreement for blue and black, but again, the state that behaved the worst in the previous slide is also the worst behaved here. Okay, so moving on. So sometimes we might see the following relation for the decay rates in early times, and sometimes we won't. So this would relate how pure state equilibration, linear response theory, and this Srednicki autocorrelation function decays to equilibrium for early times. So I guess for sufficiently simple initial conditions. So unfortunately, the arguments I've laid out don't quite work well when relating pure state equilibration to the Kubo formula or the autocorrelation function for later times. And it's largely an early time statement. So an obvious reason for this might be that we are ignoring higher order moments of our probability distribution. So for example, the short bound gives us the following inequality for the second moment. And if you follow the proof in Short's article, you would get, and you generalize it for a third moment, you would get the following inequality seen here. So now the third moment in this inequality is certainly smaller, as the trace of omega to the power of 4 is smaller than the trace of omega squared. However, this bound doesn't allow us to throw away the third moment, as if it's non-negligible, or sorry, if it's negligible, it very much could be something that we need to include, and very much could be non-negligible. So it's desirable to investigate higher moments and study how including that information about our second moments, how that can affect our probability function for our dynamics. And I forgot to put an animation on that, so we'll just go all the way there. So consider again the probability distribution function that we started with, and let us return to a general function of time t, as the method that we're about to talk about doesn't discriminate against different dynamical functions. And so the key ingredient for our method is this bound here on the moments that I said earlier. So q times g, where g is some small number, all to the power of q. So assuming we can find a bound on the moments in that form, what we can then show is the following inequality on the conditional probabilities in our probability distribution function. And what this is telling you is that if you were to pick some random time t and you were to measure your function f of t, the probability that it is delta away from its equilibrium value is exponentially suppressed, assuming that g is a sufficiently small number. Now, this bound on the moments probably isn't actually optimal. So in fact, I just showed you on the last slide for the third moment for the pure state evolution that I can find a tighter inequality, as we'll see later. if you can derive bounds on your moments that look like this equation, then the concentration bound that I show you here is general, following from the moment bound. So the key thing that you need to do is you need to find the bound on the moments, and then everything that I'll show you next follows from that. So let us continue with this general concentration bound. So to make progress analytically, we need to make assumptions on the types of models and functions that we're actually going to look at. So the functions we will work with today are the expectation value of an observable under pure state of evolution, and we will also work with the fidelity. So the assumption we make is the following. So let H be a Hamiltonian with a discrete spectrum, and let lambda Q and lambda Q prime be two arbitrary sets of Q energy levels. And what we'll say is that this Hamiltonian is generic if the following equality in 13 there, which is just a sum of energy eigenvalues, holds if and only if the two sets are equal. And so what this means is that we are assuming we have a non-degenerate Hamiltonian. We are assuming we have non-degenerate frequencies, and we are assuming that higher statements like that hold for our statement for higher sums or higher values of Q. So this is definitely a strong statement. A strong assumption. So a possible mathematical justification is that the probability of uniformly choosing a non-generic Hamiltonian is 0. But that's not a good justification. So this the usual argument given in literature is that this is expected to hold for chaotic models. Okay, so for the fidelity, we can start off with some results. In that context, we can bound the moments by the following inequality. So just a reminder, we expect the purity of the diagonal ensemble to decay exponentially fast in the system size. And this means that these moments decay to 0 quite quickly. Now, this bound allows us to write the following conditional probability. And what this tells us is that the probability of finding the fidelity being away from its equilibrium value by at least delta is less than a constant times e to the power of minus delta divided by the purity of the diagonal ensemble. So this bound doesn't scale exponentially, it scales doubly exponentially fast if we expect our purity to decay to 0 exponentially fast in system size. So we can do an analogous thing for the observable. So taking the observable A and time evolving it. Now we get the following bound for the moments, where in particular the key differences are firstly, now we again have the largest singular value in our expression, and now the purity is inside of a square root. So interestingly, the fidelity is recovered in this expression if we take A to be the density matrix of the of our initial state, and if you go through the substitution, you'll see that this bound actually behaves sort of poorer than the bound I showed you previously. So it is a different bound. So just like the fidelity, we can use this bound to show our concentration results, or use our concentration bound. And we can see that our observable highly concentrates around its equilibrium value, and that's sort of the punchline, and that's what we mean by concentration of equilibration. So note that if you try to compute this concentration bound with Short's bound that I showed you previously, you would only get an exponentially tight bound rather than a doubly exponentially tight bound. So the bound does come at the price of the assumption on the energies, but the bound does give you sort of an exponentially better bound if your system does have that property. So now that we've shown under an assumption on the energies that the fidelity and the observable's expectation value highly concentrate around equilibrium, we'd like to explore recurrences. And so the story that I've told you so far about how our quantum system starts from far from equilibrium, and then, as the name suggests, it goes to equilibrium and stays there. So this is true for most times. But the Poincare recurrence theorem, however, guarantees that at some later time t, which is guaranteed to be a finite time, our system will leave equilibrium and return arbitrarily close to its initial conditions. So the theorem is quite general, only requiring a discrete spectrum for the quantum case. So seemingly, this conflicts with our notion of the emergence of equilibrium. So the resolution to this problem, however, is intuitive. We expect that the recurrences should occur at extremely long times. The more degrees of freedom we add to the system, that should push the recurrences farther away in time. So let's formally define what a recurrence is, or in this case, a recurrence interval. We say that a recurrence has happened, writing it as t subscript delta, if for all t in the interval c subscript delta, our observable's expectation value is within u times its if it's within u of its initial condition. So we can similarly define a recurrence for the fidelity when our fidelity returns close to its initial condition as well. And of course, our main goal here is to lower bound when such recurrences happen. So what we're going to do is we're going to define the nth recurrence such that the n plus 1th recurrence is always farther away in time than nth recurrence. And we will define the average spacing of the recurrences with the following limit function, so that it is the time of the nth recurrence divided by the number of recurrences that have taken place. So this might not make intuitive sense right away, why this is a desirable quantity to investigate. So let's gather some intuition. So the dynamics of our observable or fidelity are defined by an almost period, are defined by an almost periodic function, meaning that they will have an almost period as well. So let this arrow represent the arrow of time, and we will mark recurrences with red dots. So let's say for simplicity that we have 3 recurrences for every almost period. So if we look at the sequences of the nth recurrence divided by the number of recurrences only after a full almost period, we see that we have the first almost period p tilde, which is the almost period divided by 3, then 2p tilde divided by 6, and so on. So the sequence goes to p tilde divided by 3, which is equal to 1 over the density of the recurrences that we see. And sorry, so if this number is a very big number, then we expect the density to be a very small number. We don't expect a lot of recurrences. So in the end, we get this general bound for the fidelity. The recurrence time is always larger than this formula. So this bound is rigorous and only relies on the assumption of the energy eigenvalues I showed you earlier. And again, if we look at the purity of the diagonal ensemble in the denominator of the argument, we expect this to be double exponentially scaling. And so for more intuitive scaling, if we expect the recurrence to go quite close to the initial conditions, then we expect the recurrence time to scale something like this. So we see in the exponential a big omega notation, which tells us that this is a lower estimate. And the argument could scale faster than this, where the argument is the inverse of the purity, and sigma here is the variance in the energy. And note that this matches previous estimates, which indicates that our results should be close to optimal. So analogous results for, I think this was supposed to be 45 minutes. So I feel like I'm approaching my time here, so I'll go a little fast. But analogous results for the observable. In the end, if we have a recurrence that's very close to the initial conditions, then we get the following equation, where again we have in our argument trace of omega squared, or negative half, and the constant outcome becomes the integration timescale. And so we can go through free models as well. So with some assumptions.
I'm sorry, for free models.
Yeah.
What is the assumption for free models?
So it's also quite a strong, basically to get the right dephasing for the analytics to work. We assume that the coupling matrix M is a generic matrix. And then we also
like a random, in a Hermitian random matrix.
yeah. And then we assume that that our model is extensive, so this excludes localized models.
Yes.
As well. And that's our assumptions. And then through there, you get concentration bounds that instead of being doubly exponential, you get exponential scaling with system size.
Okay, no, sorry, but
Yeah.
so with these assumptions that you make, are you able to prove this other assumption on the energy levels, or you also make that as a separate assumption?
Sorry,
So yeah,
this is an assumption.
and you make this assumption also for the free system.
Yes. Yeah. Well, for the coupling matrix M. Okay, so the single particle spectrum. Yeah.
Yes.
Yeah. So in general, this is basically to make the dephasing work, to make bounding the moments possible. And then we get these types of concentration bounds that are now exponential. And in this case, we also we're looking at the single particle propagator and a local observable here. Yeah. Okay, so I have a slide with the. So that's the summary for recurrence timescales for the free case. Okay, and that's it. So thank you for listening to me.
Oh, that is here.
Okay.
Okay, so any questions?
So I guess where the system size came in for the pre-models was clearer. Is there any way to relate the bounds to the system size generically?
What do you mean by everything?
Well, for the before you start talking about pre-models.
So then, yeah, so that would be. Yeah, so if we look at something here, you have trace of omega squared, which we expect to go, so you expect that to be like d to the negative of the volume of the system.
Okay, right.
Yeah. So it'd be doubly exponential in system size. Yeah.
So is that obvious why that becomes just exponential?
Why is it different from free systems?
Well, it's different for free systems because basically the effective Hilbert space size is linear in the number of lattice sites. And then for a generic non-integrable model, it's like, you know, d to the n by d to the n, basically.
So this diagonal, this diagonal ensemble, the diagonal density matrix is crucial. Yeah.
Yeah.
You want it to be as spread out as you can.
Yeah, so we want as many eigenstates as possible to participate in the dynamics.
So the more concentrated, the less fast, or in this case, the quicker the renewals, the less, your time scale separation gets worse.
Yeah, exactly.
But it's still exponential, right? Genetically.
Yeah.
Even if I'm not infinite temperature.
Yes,
It's
exactly.
it's still exponential in general.
Yeah, it might not be as fast. It might not go to zero as fast as the Hilbert space, but yeah. Or
So that's basically the key thing that's giving you like these good results.
Yeah, the key thing, yeah, security of the diagonal ensemble is the key. Yeah, that's the crux there. Yeah. Yes.
I have a bit more stupid question, which is this. When one talks about equilibration, so the usual statement is that the expectation value is thermal.
Yeah.
But now, if I think about classical equilibration, the statement is that in the stationary state, I sample states according to the, thermal distribution.
Yeah.
Is there an equivalent statement here that goes beyond just the expectation value?
So the way you justify that is the eigenstate thermalization hypothesis, which I believe you can use to you can prove quantum ergodicity. If that's where you're.
Yeah, what I'm saying is that the usual ergodicity is that over time I'm sampling the state, the thermal distribution.
Yeah.
So visit state is by weight time, which is essentially the time it took you to equilibrate.
Yeah.
I sample again. I find a state that is distributed with e to the minus b.
So in the quantum regime, the individual energy eigenstate will have the exact same expectation value as an appropriate thermal ensemble.
So there is a way to formulate this kind of ergodic visiting sampling the states.
No, perhaps it's a little different than that. Yeah. Okay.
So I have a final question on the seal of free case.
Sure.
So in that case, I guess that one can actually find a matrix for which the assumption holds for sure. So the assumption on the other side. So can I show in this case that I can construct a matrix and such that this will certainly hold?
So the answer to that is I don't know. So as you know, we're looking at another class of Hamiltonians to see if they have a property like this. And initial evidence suggests that despite this being a very popular assumption in the literature, it might not be a warranted assumption.
Because I guess in the free case, well, I would be very confident that one can at least cook up some matrix and
Where that holds.
for which this will hold.
I see. Well, I suppose you could just yeah.
Yeah.
But you also require it to be like a random, to have like random matrix.
Yeah, exactly. That's a good point. So what are the other assumptions on the matrix again? So apart from this, what are the other assumptions on M that are key to prove the result in the free case?
So this matrix is the matrix that diagonalizes it.
Right.
So you need the single particle vectors to have this property. So the single particle vectors need to be extensive. So they can be localized.
Right. So if there are no more questions, so no questions from the audience online. Okay. So then I think we can thank Jonathon again.